Section 6.13. The dependence of the extent of reaction on temperature and pressure. In this section, we will see how the reaction shifts or responds when we change the temperature or pressure. First, let's review this. If the Gibbs energy of reaction is 0, the reaction is at equilibrium. If the Gibbs energy of reaction is less than 0, then the reaction will proceed in the forward direction. If the Gibbs energy of reaction is positive, then the reaction should proceed in the reverse direction to further lower the total Gibbs energy of the reaction mixture. Then how does the equilibrium shift as the temperature or pressure is changed? When the pressure is a constant, let's change the temperature. We learned this equation. The logarithm of equilibrium constant at temperature 2 minus the logarithm of the equilibrium constant at temperature 1 is equal to negative enthalpy of reaction over R times 1 over T2 minus 1 over T1. We can combine this two. When we combine this two, we get T1 minus T2 over T1 times T2. And then there's another negative sign here. So the result is delta H over R times T2 minus T1 divided by T1 times T2. So if this delta H is positive in an endothermic reaction, then when T2 is greater than T1, Kp2 is greater than Kp1. If we have an exothermic reaction, delta H here is negative. And then when T2 is greater than T1, Kp2 is less than Kp1. So for endothermic reactions, Kp increases as temperature increases. If we have this enthalpy of reaction less than 0, then Kp decreases as temperature increases. If the reaction is neither endothermic nor exothermic, then Kp is independent of temperature. But this is very rare. How does the equilibrium constant of mole fractions depend on pressure? So first, I want to emphasize this. K sub P, the equilibrium constant of pressures, does not depend on pressures. So it's weird. But if you think about this, the Gibbs energy of reaction in a standard state is negative RT ln Kp. And you can see the Gibbs energy of the reaction in a standard state is simply the Gibbs energy of formation of the products minus the Gibbs energy of formation of the reactants, both in the standard states. And therefore, Kp actually is independent of the pressure of the reactants or the products. So that's weird. However, K sub x does depend on pressure. All right, let's write out this K sub P is equal to K sub x times the total pressure over P naught to the power of delta nu. Delta nu is the change of the coefficients of the gases. So again, ignore the solids, ignore the liquids. You just count the coefficients of the gases and take the difference between the products and the reactants. And then K sub x is K sub P times this P is the total pressure of the gas mixture, the chemical mixture over P naught to the power of negative delta nu. So again, K sub P is independent of the total pressure. Again, because of this equation over here, this guy is independent of the pressure. This guy is the Gibbs energy of formation of the products minus the Gibbs energy of formation of the reactants. Both the products and the reactants should be in their standard state. So it's regardless. It does not depend on the total pressure of the actual reaction mixture. RT do not depend on the pressure either. Therefore, this K sub P does not depend on the total pressure. And therefore, this K sub x does depend on the pressure. This K sub x is proportional to the total pressure to the power of negative delta nu. So that's interesting. If delta nu is less than 0, that means we have fewer gases on the product side. Then as the pressure increases, the reaction proceeds forward. So when the total pressure increases, the reaction proceeds toward a direction to reduce the number of moles of gases. Now when this delta nu is greater than 0, what does that mean? That means you have more gases on the product side you have fewer gases on the reactant side. And then, when the total pressure increases, the reaction proceeds backward again toward the side with fewer gases. So just imagine, you can just imagine, when we increase the pressure, okay, when we compress the chemical system will shift to the side with fewer gases. What if this delta nu is equal to 0? And then this K sub x is independent of the total pressure. Again, you just plug in this delta nu is 0 here, you'll see K sub x is equal to K sub p. Both are independent of the pressure. So those are quantitative analysis, but really it's just this Le Chatelier's principle. If a chemical system at equilibrium experiences a change in concentration, temperature, partial pressure, or the total pressure of all species that are involved in the reaction, then the equilibrium shifts to counteract the imposed change, and a new equilibrium is established. I want to emphasize this part, the total pressure of all species that are involved in the reaction. So let's say we have a container, a 1 liter container, and then we have a reaction inside. We have carbon monoxide, CO, react with oxygen to produce CO2, carbon dioxide. And then if we introduce, for example, argon in the same container, all right, the total pressure of the mixture does increase, right? So because if you have more gas, more argon in the container. However, the total pressure of the chemicals that are involved in the reaction remains unchanged. So the total pressure of CO, O2, and CO2 remains unchanged. And in this case, the introduction of argon has no impact to the chemical equilibrium.